Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. BS Physics, Semester 1, Mechanics 1, Course Code Physics 1103, Lecture number 16, Chapter number 5, The Newton's Laws of Motion. This lecture, named as The Newton's Second and Third Laws of Motion. I am talking to you, Rashmat Ali, Assistant Professor of Physics, Khaja Fareed Government Postgraduate College, Rimia Khan. Dear students, the material of this lecture has been taken from Physics for Scientists and Engineers by Survey Javed. The second book, Fundamentals of Physics, Halliday and Resnick, and the Gerald Walker. First of all, the main contents of this lecture: frame of reference, mass and weight, Newton's second law of motion, the gravitational force and the weight, Newton's third law of motion. Frame of reference. Frame is any three-dimensional body, and reference according to which the measurements are taken. In general, the definition of frame of reference can be quoted as any set of coordinate axes relative to which measurements are taken is called frame of reference. Any three-dimensional body such as earth, bus, car, or any person can be considered as the frame of reference. If we see the diagram, the frame of reference is like this. This is a three-dimensional coordinate axis, x, y, and z, and a body shown in the box. If it moves, then its measurements such as displacement, velocity, acceleration can be measured relative to this frame that is from the origin in any time t. Frame of references has the two types: the inertial frame of reference and the non-inertial frame of reference. The inertial frame of reference: any frame of reference that is at rest or moves with a uniform velocity. In other words, any frame of reference, any body having zero acceleration is called inertial frame of reference. When we travel on a moving train with constant velocity, the train is said to be the inertial frame. So, there are so many examples of inertial frame of reference. If we take the earth is revolving around the sun with uniform speed, then it can be considered as an inertial frame of reference. Since in circular motion its velocity changes, so it can also be called as a non-inertial. But velocity change is a small with direction, so acceleration is small. That can be neglected in general, so we can call it as the inertial frame of reference. Similarly, the non-inertial frame of reference, F dot O dot R is abbreviated for the frame of reference. So, in contrast to inertial frame, we can state it as any frame of reference moving with changing velocity or with acceleration. Changing velocity means increasing or decreasing velocity. It can be called as a non-inertial frame of reference. Earth, as I explained it earlier, is a non-inertial since in circular path its motion is considered, so its acceleration is very small, so it can also be treated as an inertial frame of reference. Inertia. In the last lecture, in the first law of motion, we have also called the first law of motion as the law of inertia. What is the inertia? The property of matter that resists any change in the state of rest or motion with uniform velocity is called inertia. In Urdu, we call it a jamood, means stay at one place, whether in velocity or in rest. If we switch on the ceiling fan, we see the ceiling fan gets uniform velocity after a certain time because due to inertia, rest inertia, the fan is resisting the motion. If the fan is switched off, the electrical connection gets off at once, but it comes to rest with a certain time because it is resisting to come to rest. How inertia can be measured? Mass is qualitative measure of inertia. If a body has small mass, then it has small inertia. And if a body has large mass, it would have a large inertia. So it is necessary to consider the mass. What is the mass? The quantity of matter is called mass. How much matter is present in the body, that will be its mass. If we want to measure the matter of a body, means we are measuring the mass. Mass is the inherent property of the matter and is independent of the surrounding and method of measurement. So we can say that mass is the fundamental property of matter. Mass specifies that how much resistance a body have to change its velocity. If a small body, we can move it easily because it has a small resistance, small inertia. If there is a large body at rest, so it must have large inertia, so it is difficult to move it. And similarly, if a small body moving, we can easily stop it because it has a small inertia. If a large body is moving, suppose a truck, a bus, a car is moving, it is difficult to stop it because it has a large mass, large inertia, and large resistance to stop it. Going forward, mass. SI units means System International Units of Mass is kilogram. kg is its abbreviation. The greater is the mass, the lesser is the acceleration for an applied force. Acceleration and mass and inertia are inversely for same force acting on two bodies of masses m1 and m2 with acceleration a1 and a2, we can write the ratio m1 over m2 would be equal to a2 over a1. This shows that mass is inversely proportional to acceleration. The difference between mass and weight, we have studied this difference in the junior classes such as 9th class. Mass and weight are oftenly misconcepted. When we say that a body has 5 kg, it means it is a mass. But in normal life, we say this is a weight. So it is necessary to differentiate mass and weight. I have made the differences tables in examination. The question may be put as differentiate between mass and weight. So, similarly, if a question is asked, define mass, define weight, we can use these points easily. So, the difference, the quantity of matter contained in a body is called mass, whereas weight, the gravitational pull of Earth on the body is called weight. How much the gravity pulls a body is its weight. Mass determines the amount of acceleration under the action of force, whereas weight determines the force with which the Earth attracts the bodies towards the center of Earth. Another definition and the difference, we can find the mass mathematically as m is equal to f over a, where f is the force and a is acceleration, and measured in kilograms. Whereas weight is W is equal to mg, and it is measured in newtons. Mass is a scalar quantity, whereas weight is a vector quantity. Mass is constant everywhere and measured by physical balance, whereas weight changes from place to place on the surface of Earth and above from the surface of Earth. It is measured by spring balance. Physical balance and spring balance are two balances. Spring balance is vertically hanging down. Gravity easily acts upon it, and physical balance have the two pans One contains the standard mass and the other contains the unknown mass. Now the Newton's second law of motion. First of all, we want to see the statement. One thing remember, dear students, the difference between first law and second law. When we quote the first law of Newton, means no force is present there, or means force is zero, means body is at rest or moving with uniform velocity, means acceleration is zero. Sometimes forces are acting on the body, but even though the body is at rest, it means that the force acting on the body are the balance forces. These forces cannot change the state of body. State means here the motion or rest. If applied force have such an amount that it is able to change the state, whether rest to motion or motion to rest, then it means it is an unbalanced force in an external force. So Newton's second law of motion is the case of force when force is unbalanced. We can state the Newton's second law as when a force acts on a body, it produces acceleration in its own direction. Acceleration such that the acceleration is directly proportional to the magnitude of force and inversely proportional to the mass of body. This law specifies the presence of force and its measurement, whereas the first law specifies the absence of force It is imperative to determine the correct net force on the object. Then we can find the magnitude of force. When there are more than one force acting on the same body from different directions or the same direction, the forces are resolved into their components. So, we can say that F sigma Fx is equal to max, means all the forces acting along x-axis are acting along the horizontal axis. Similarly, the forces along y-axis, the resultant force will be sigma Fy equal to my. Similarly, in the third direction, z-axis, sigma Fg equal to miz, where ax, ay, az are the accelerations and m is the mass of body on which the forces are acting. There are so many examples of Newton's second law in daily life. We see long jump or high jump, two athletic events. When an athlete runs and jumps from a bar or a long jump, where the jumper has to fall, some soft material is placed there because force is acting on the jumper and the acceleration is produced. If soft material is not placed, the jumper can hurt. Similarly, while packing glass material, mud pots, some soft foam is placed in between them to avoid them from breaking due to Newton's second law of motion. Force, as we have seen in the above relation, F is equal to ma. So this mathematical form shows that force can be measured. The unit system of force in different systems, the units and their interconversions are given here. In SI units, the unit of force is Newton. Newton is the name of scientist because Newton has a great work for the force. But here we see that Newton, when we write it as a unit, then we use the first letter small, and when we use the symbol, then we use the first letter N capital. According to the above formula, 1 Newton is equal to 1 kilogram and multiplied by 1 meter per second per second. We can define Newton as the force acting on a body of mass 1 kg if able to produce an acceleration of 1 meter per second, then the force would be called as 1 Newton. Similarly, the unit of force in CGS system is dyne. 1 dyne is equal to 1 gram multiplied by 1 centimeter per second. Again, 1 dyne can be defined as the force that can produce an acceleration of 1 centimeter per second on a body of mass 1 gram. The force is said to be 1 dyne. Dyne and Newton are related. Newton is a bigger unit. It can be related with dyne as 1 Newton is equal to 10 raised to power 5 dynes. We can prove from the above formula of unit. Kilogram contains 10 raised to power 3 grams. Meter contains 10 raised to power 2 centimeters. Second is same in both. If we calculate the 10 raised to power 3 and 2, it becomes 10 raised to power 5. That is given here. And the remaining unit will become gram centimeter per second square, and 1 gram centimeter per second square is a dyne. So 1 Newton is equal to 10 raised to power 5 dynes. Similarly, the US customary in daily routine of US, British and other countries too, this system is also called as British engineering system. In some part of the world, this unit is even used now. The unit of force is pound. LB is noted here. So 1 LB is equal to 1 slug multiplied by 1 feet per second Here slug is a unit of mass and feet is unit of length. This unit of pound is derived from the system that is also called FPS, as we have told you, SI, CGS, so FPS, F means foot, and P means pound, and S is a second. The next article is the gravitational force and the weight. Gravitational force is what? We can define it as the attractive force exerted by Earth on an object is called gravitational force. Fg can be symbol of this gravitational force. This force is directed towards the center of Earth, and its magnitude is called weight of the object. So it means that gravitational force and the weight are the same, only the difference is direction. A freely falling object experiences an acceleration g acting toward the center of Earth. Applying the Newton's second law of motion, that is sigma F is equal to ma, to a freely falling object of mass m with acceleration a equal to g, then sigma F would be equal to Fg. Fg gravitational force, so we can write it as Fg is equal to mg. Gravity, a picture from the book is shown here. The value of g is different at different bodies. A man, an astronaut, is landed on the surface of moon as he wears a space suit. Man has landed on the moon. If we compare the gravities, acceleration due to gravities, the value of g on the surface of Earth is the average value 9.8 meters per second, and on the moon the value of g is 1/6 times of value of g on the Earth. Value of g of moon is 1/6 of value of g on the Earth. So, moving forward, masses has two types. One is gravitational mass, and other is inertial mass. The mass that determines the magnitude of gravitational force is called gravitational mass, and the mass that determines the magnitude of applied force is called inertial mass. We can see the formula. M is equal to Fg over g, whereas inertial mass M is equal to F over A. Now moving towards the next lecture. Next article, Newton's third law of motion. Remember, my dear students, first law, again I am giving you the small comparison between the three laws of motion. First law states the absence of force. Second law shows that presence of force. In Newton's third law is the example of force, or in other words, if force acts on a body, what is the response of the body on which the force acts? This is very simple law, simple term. That is, action and reaction are always equal but opposite in direction. If two objects interact, the force F12 exerted by object 1 on object 2 is equal in magnitude and opposite in direction to the force F21 exerted by object 2 on the object 1. That is, we can say it as F12 is equal to minus F21. This law indicates that the property of forces always exist on the in the pairs. Means if there is some action, it is necessary it must have some reaction force. The action-reaction force between two bodies is shown in the figure. The two forces in the two bodies and their directions are shown here. This is like a gravitation force acting on the body. So we can quote it as an example of Newton's third law of motion. There are many examples of Newton's third law in our daily life. Mainly the three examples are quoted here in this lecture. So the first example I am quoting here is the force of gravity on a freely falling body that is acting on downward. The force acting on a freely falling projectile is a gravitational force exerted by Earth on the projectile. That is, Fg is equal to FEP, means force of Earth on the projectile. E is the abbreviation subscription for the Earth and P for the projectile. And at the magnitude of this force is mg. This is the gravitational force. The reaction to this force is a gravitational force exerted by the projectile on the Earth. So we can say the force on the Earth and the projectile both are equal in magnitude but opposite in direction. That is, FPE, force of projectile and Earth, is equal to minus FEP, force of Earth on projectile. We have studied the projectile motion in the previous chapter. So F is in boldface, where P and E are subscriptions. Force is a vector, so we use here the boldface letters. The second example is very common example in our daily life. The hammer strikes on the nail to put it into the wall. Here again, this picture represents the various stages of hammer and exerting a force FHN on the nail, as the nail also exerts a force on hammer that is FNH. These forces we can see easily are equal in magnitude but opposite in direction. The both blue colored arrows have the same length, that is the equal magnitude, and the both arrows are in opposite direction. Means both forces are equal but opposite in direction. The hammer on the nail, the action is equal to the magnitude and opposite the force FNH exerted by the nail on the hammer, the reaction. This latter force stops the forward motion of the hammer when it strikes in the nail. Another example from our daily life experience: the earth exerts a gravitational force Fg on any object if the object is computer monitor at the rest on the table. The reaction force to Fg is Fem, means force of earth on the monitor exerted by the monitor on the earth. Mathematically, the same equation appears here. Fme is equal to minus Fem. We can see easily from the figure, as a monitor placed on the table as to rest position, we see that the force of gravity is acting downward, that is the force of earth on the monitor. Whereas the monitor also exerts force on the tabletop, Fmt. These two reaction forces on the monitor and the table, N is the normal force. We can also say that the table is also exerting a force on it. In other diagram, we can see these two forces are in opposite direction, Fg and Fme, force of monitor on the earth. So, we have seen many forces. The monitor does not accelerate because it is held up by the table. The table exerts force on the monitor, on the upward force is N is equal to Ftm, called the normal force. Dear students, this lecture comes to an end. So, thanks for listening and watching the lecture with patience. Allah Hafiz.